Welcome to This Explainer. We're going to be exploring one of the most absolutely fascinating mysteries of our entire universe today. Because when you look around our world right now, it seems, well, meticulously made just for us. I mean, we've got abundant food, a perfectly breathable atmosphere, these sprawling, beautiful oceans. In this vast universe, Earth is literally the only place we currently know of where humans can just survive without any outside help. But if we rewind the clock 5 billion years, taking it right to the edge of the Milky Way galaxy, our beautiful blue home didn't even exist. There was just nothing. So how on earth did we get from an empty void to a planet completely teeming with life?
To answer that, we've got to unravel a massive puzzle, and it actually starts with a pretty incredible space mission. Okay, let's dive into this cosmic detective story. Back in January 2005, NASA launched a highly unique probe called Deep Impact, and its sole mission? To answer one massive question: where did Earth's water actually come from? This probe traveled a mind-boggling 270 million kilometers just to reach a comet known as Tempel 1. Hidden inside this distant, icy rock were secrets that scientists had been hunting down for centuries. But to really understand why Tempel 1 was the key to everything, we first need to jump way back, 5 billion years back, to a time before our sun even had a solar system.
Because before Earth was here, there was just a molecular cloud. Picture this swirling, chaotic mixture of dust particles, gases, sand, silicon, and a bunch of different metals just floating out there in deep space. All of these materials were actually the scattered remains of ancient dead stars that had burned through all their fuel and exploded in the early universe. Now, back in the 1700s, philosophers like Immanuel Kant hypothesized that stars and planets were born from these exact types of clouds, and it was a brilliant idea. But it wasn't until the 1970s and 80s, right when we invented advanced radio and infrared telescopes, that astronomers could finally peer into these dense dust clouds and literally prove it.
What's truly unimaginable here, though, is the sheer scale we are talking about. This molecular cloud spanned 100 light years across. To put that into perspective, if you took the distance between the Earth and the Sun, well, this cloud was 6 million times larger than that. Inside this massive expanse, gravity started to work its magic. Heavier particles began pulling lighter particles right toward them, and as they violently collided, they generated immense energy and heat. This swirling center grew hotter, faster, and much denser over millions of years until, boom, it ignited into a massive fireball. That fireball became our sun. But what about all the leftover dust and gas? Well, that just kept swirling around our brand new star, setting the perfect stage for the planets.
So you might be wondering, how does dust just floating in a huge cloud actually turn into a solid planet? For a really long time, this process totally baffled scientists. But in March 2003, astronaut Don Pettit conducted this really cool experiment aboard the International Space Station that gave us the answer. He injected water bubbles into a plastic bag, added some dissolved salt, and then just spun it around in zero gravity. And this brilliantly illustrates what happens. Because without Earth's heavy gravitational pull masking the really subtle forces, those tiny salt particles naturally began to attract one another and clump together. This zero-gravity experiment perfectly mirrors what happened in our early solar system. In the absolute vacuum of space, particles traveling in the same direction just naturally attract and stick to one another.
So flash forward to about 4.5 billion years ago, and those microscopic clumps of dust and salt around our young sun just kept growing. They went from tiny pebbles to massive 1-kilometer-wide mountains floating in space. And once they reached the size of a mountain, their own gravity became incredibly strong. They basically started acting like giant cosmic vacuum cleaners, sucking up all the surrounding dust and rock. Over the next 3 million years, this process birthed about 20 early planets. But as you can imagine, 20 planets in one single solar system is a total recipe for chaos. Their gravitational pulls constantly dragged them into each other's paths. They violently smashed into one another, merging and growing bigger with every single collision until only a few survivors were left standing: Mercury, Venus, Mars, and our Earth. But listen, early Earth was absolutely nothing like the paradise we know today. It was a terrifying, boiling fireball of molten rock. And it faced a massive, immediate existential threat: deadly solar storms. The sun was constantly blasting out this intense, lethal radiation that could easily strip away a planet's young atmosphere and destroy literally any chance of life taking hold. We can actually see the tragic result of this right next door on Mars, where those violent solar storms essentially sterilized the entire planet. So why did Earth survive while Mars didn't? The answer, surprisingly, lies in Earth's intense heat. Because early Earth was essentially entirely melted, super heavy metals like iron and nickel were able to sink right down into the absolute center of the planet's core. And that sinking iron is literally what saved our existence. Because the Earth was spinning, all that heavy molten iron in the core began to swirl around. And geophysicists know that swirling molten iron generates a magnetic field. Thanks to the sheer massive quantity of iron right in our core, Earth generated a ridiculously powerful shield called the magnetosphere. On the side facing the sun, this invisible shield stretches out an incredible 370,000 kilometers. I mean, that is almost all the way to the moon. It safely deflects the sun's lethal radiation. At the north and south poles, where the field is just a tiny bit weaker, a little bit of this radiation slips through, but it harmlessly interacts with our atmosphere to create those stunning auroras, the northern and southern lights. So Earth survived the sun's deadly radiation, right? But it was still an incredibly hostile place. It actually had to go through one more major, catastrophic event to become habitable. To understand this, we've got to look back at the Apollo missions in the 1960s. When American astronauts brought rocks back from the moon, scientists were completely blown away. Because these rocks didn't look like normal space rocks. They looked intensely burnt. And even crazier, further analysis revealed that the rocks shared the exact same oxygen isotopes as rocks found right here on Earth. This proved beyond a shadow of a doubt that the moon wasn't just some random rock captured by Earth's gravity. It was literally violently burned and ripped right out of the Earth itself.
This brings us to a terrifying moment in our planet's history, known as the Theia impact. While our Earth was slowly starting to cool down, this rogue, Mars-sized planet named Theia was on a direct, unavoidable collision course with us. When Theia smashed into Earth, the release of energy was just incomprehensible. Burning debris from both Earth and Theia was blasted way out into space. Over thousands of years, just like the dust in the molecular cloud, this debris clumped together in orbit to form our moon. And fun fact, back then, the newly formed moon was incredibly close to us. It would have appeared 15 times larger in the night sky than it does today. It's actually been slowly drifting away from us at a rate of about 1.5 inches per year ever since. But this collision didn't just give us a cool moon in the night sky. So the crucial point is, the sheer immense force of Theia slamming into us literally knocked our entire planet off its axis. Before the impact, Earth was spinning straight up and down. But after the impact, it was permanently tilted at an angle of exactly 23.5 degrees.
And that specific 23.5-degree tilt, it triggered a massive cause and effect chain that makes life completely possible today. Because we're tilted, different parts of the planet lean toward the sun at different times of the year, and that gives us our diverse seasons. This brilliantly prevents the Earth from just having one extreme uniform temperature all year round. It gives us our vital monsoon rain cycles, which constantly deliver fresh, clean drinking water right through our rivers. And on top of that, our newly formed moon's gravity began pulling on the Earth, creating our ocean tides. These tides are basically a giant cosmic stirring spoon, constantly distributing vital nutrients all across the oceans so marine life can thrive. But there's a catch.
Section 3. The water delivery system. Because as we all know, ocean tides are absolutely useless without actual water. See, since early Earth was a boiling fireball, any initial water that might have been here would have instantly vaporized into space in like less than a second. Early Earth was bone dry. So, to figure out how our massive, deep oceans actually got here later on, let's go right back to where we started, that NASA Deep Impact probe from 2005. The probe finally caught up with Comet Tempel 1. And on July 4, 2005, the probe released a 350-kilogram solid copper impactor directly into the comet's path. This impactor smashed into the comet at a staggering speed of 38,000 kilometers per hour. The collision blasted a huge crater into the comet, and the radio telescopes on the main probe instantly captured the explosion. By meticulously analyzing the light from that explosion using spectroscopes, scientists made a monumental, absolute game-changer of a discovery. Deep inside Comet Tempel 1, completely hidden beneath all that rock and dust, was a massive reservoir of water ice. This proved that comets floating way out in the asteroid belt were essentially giant frozen water bottles. We finally knew for sure that water existed in space. But wait, the asteroid belt is incredibly far away from Earth, so how did millions of these frozen water comets leave their super stable orbits and actually find their way to our dry, barren planet? Well, in the asteroid belt, these comets had these really stable, perfectly circular orbits around the sun. But they encountered a massive disruptor. Enter Jupiter.
Jupiter is the largest planet in our solar system with a gravitational pull that is vastly more powerful than Earth's. And importantly, Jupiter orbits right on the absolute edge of the asteroid belt. So as Jupiter moved, its immense gravity grabbed hold of these comets. It warps their perfectly circular paths, stretching them way out into long, oval shapes, what astronomers call elliptical orbits. This stretched-out elliptical path dragged the comets out of the safe zone of the asteroid belt and sent them careening wildly toward the inner solar system. Jupiter essentially acted as a massive gravitational slingshot. It hurled millions, possibly even billions, of these ice-filled comets directly into the path of Earth. And as they smashed into our slowly cooling planet, all that ice melted, eventually filling up the giant rocky basins of our world to create the literal oceans we have today. Jupiter, the giant gas planet, was the ultimate cosmic water delivery system.
So let's tie this whole crazy timeline together. 5 billion years ago, a dusty molecular cloud begins to collapse. 4.5 billion years ago, a massive collision with Theia violently knocks Earth off its axis, giving us seasons and our moon. And then, 4 billion years ago, the water finally arrives. Now you might be wondering, how do we know the exact timing of the water? Well, geologists study this amazing mineral found in ancient rocks called zircon. Zircon absolutely requires water to form. And because it naturally contains tiny traces of uranium, we can use radioactive decay to date it perfectly. It's like a tiny clock. And every sample of early zircon ever found on Earth dates back exactly 4 billion years. This proves, definitively, that our oceans arrived precisely 500 million years after the Earth was actually born.
It's truly amazing when you step back and look at it. The sheer cosmic luck involved here is just staggering. Earth's temperature finally dropped to a manageable 100 degrees Celsius. We somehow survived those early deadly solar storms. We got the perfect 23.5-degree tilt to give us seasons. We got a moon to stir our brand new oceans. And Jupiter kindly slingshotted millions of icy comets right at us to give us our water. The stage for life was officially set. But wait. There is still one incredibly vital piece of the puzzle missing here, because even with the perfect temperature and these endless, vast oceans of water, early Earth's atmosphere was still completely, utterly toxic. There was absolutely no oxygen to breathe, none. So if the water came from comets and the seasons came from a giant planetary collision, where on Earth did the oxygen come from? Well, that is a wild mystery that might just change how you view life itself, and it's one we are definitely going to have to explore next time.